Hi, everyone. Welcome to session one of the Great Lakes Coastal Wetlands webinar series hosted by Environment and Climate Change Canada and Toronto and Region Conservation Authority. My name is Sharon Lamb, and it is my pleasure to moderate today's webinar. I'm a project manager with the Ecosystem and Climate Science team at Toronto and Region Conservation Authority, and I'm joined by an amazing group of colleagues in both ECCC and TRCA, some of whom you'll meet over the course of this afternoon. Let me begin by taking a moment to respectfully acknowledge that all of us at this virtual meeting, no matter where we are located on land that has been home to Indigenous nations since time immemorial. We respectfully acknowledge that the lands we are situated on are traditional territories and treaty lands, in particular, those of the Mississaugas of the Credit, the Anishinaabe of the Williams Treaty First Nations, the Huron-Wendat, the Haudenosaunee, and are now home to many diverse First Nations, Inuit, and Métis peoples. We appreciate and respect the history and diversity of the land and are grateful to have the opportunity to work and meet in this territory. And we are honored to be joined by representatives of Indigenous organizations at today's webinar. Let's now go over some quick housekeeping notes. Today's session is being recorded, and a copy of the recording and slides will be shared with all of you in a couple of weeks following the completion of the webinar series. All participants are muted and video disabled to minimize disruption and save bandwidth and emissions. Please use the Q&A box at the bottom of your Zoom control panel to post questions throughout today's session. You can also upvote others' questions in the Q&A. To share comments, please use the chat, and thank you to all of you for sharing with us in the chat your name and where you're calling from today. Closed captioning is available in English, and you can enable or disable this by clicking the CC icon at the bottom of your Zoom control panel. If you encounter any technical issues with Zoom, please send an email to Jessica for support. And with that, let's now take a look at what we have planned for you over this week-long 5-part webinar series. The first 2 webinar series, today and tomorrow, focus on the sharing of the results of Environment and Climate Change Canada's Great Lakes Coastal Wetlands Climate Change Vulnerability Assessment. Today's session is focused on the results of the climate, lake level, and wetland response modeling developed by Environment and Climate Change Canada. And session 2 tomorrow will focus on the remaining results from the vulnerability assessment, including wetland sensitivity, adaptive capacity, and overall vulnerability. Over the course of sessions 3 to 5 from this Wednesday to Friday, we will explore different climate change adaptation strategies and options to enhance the resilience of Great Lakes coastal wetlands with guest speakers from across the Great Lakes Basin. So I hope that you can join us in these upcoming sessions, and hopefully we will see you then. Through these webinars, we hope to engage coastal wetland practitioners, describe Environment and Climate Change Canada's vulnerability assessment, modeling and analysis, share the results of the climate and water level projections, wetland sensitivity, adaptive capacity, and vulnerability, and explore best adaptation strategies and options to enhance coastal wetland resilience. With that, let's take a closer look at what we have in store for you today. We'll begin with a presentation by Greg Mayne, who will provide an overview of Environment and Climate Change Canada's Assessing and Enhancing the Resilience of Great Lakes Coastal Wetlands project. We will then hear from Dr. Frank Seglenieks about how the climate and water levels are expected to change in the Great Lakes Basin. We'll then take a quick 5-minute break and reconvene for our last set of presentations by Dr. Marianne Bachand and her team on evaluating the response of Great Lakes coastal wetlands to the projected changes using an integrated ecosystem model. We will be taking a few questions after each of the presentations as time allows, and we'll also have a collective panel discussion at the end. So please input your questions in the Q&A throughout the presentations, and where possible, please direct your questions to specific speakers. I will now invite Greg to please share his screen while I provide a brief introduction to Greg. Greg Mayne is the Habitat and Species Unit Head with Environment and Climate Change Canada's Great Lakes Ecosystem Management Section. Greg began his career as a biologist with the province and later as wildlife toxicologist with the Canadian Wildlife Service. since 2004. Greg has also co-developed various Great Lakes plans, including lake-wide action and management plans, biodiversity conservation strategies, baseline coastal habitat surveys, initiatives for community-based action, and most recently on coastal wetland vulnerability, resilience, and adaptation. And Greg, I see that your presentation is now up and in full presentation mode, so I'll pass the floor now to you.
Thanks, Sharon. Good afternoon, and thanks everyone for joining our exciting 5-part webinar series. I'm happy and frankly relieved after 4 or 5 years to kick things off and introduce a study that we call Assessing and Enhancing the Resilience of Great Lakes Coastal Wetlands. For you Great Lakes observers and resource managers, this study is supported by Canada's Great Lakes Protection Initiative and helps to address our joint domestic and binational science priorities made under the Great Lakes Water Quality Agreement and the Canada-Ontario Agreement on Water Quality and Ecosystem Health. On a personal note, wetlands have always been special places to me. I grew up tramping through them, and my career has allowed me to dabble in wetlands from time to time through contaminants monitoring, biodiversity conservation, management planning, and of course this study. So on behalf of our wetland working group, we hope that you enjoy the presentations and appreciate our synthesis of methods and results. Before moving on, I'd like to share some terminology. While there's many definitions and interpretations out there, resilience in the context of our study refers to a trait that represents the capacity of a wetland to cope with climate change disturbance or trends in ways that maintains its basic identity and functions to provide ecosystem services. It's a very theoretical concept. It's complex and untested, at least in the context of the Great Lakes. You'll see that our approach was to understand vulnerability firstly, the inverse of a resilience, of course, which is defined for you on this slide. Vulnerability is equally complex. However, our team worked hard to operationalize it and understand the processes that determine whether coastal wetlands are likely to experience harm due to climate change. To simplify our work, we set out to answer some basic questions. First, what climate drivers and projections should wetlands be resilient to? Secondly, what are the plausible wetland responses and vulnerabilities to climate change? And lastly, how can we collectively enhance wetland resilience through adaptation so that we can cope, or they can cope, I should say, and persist in the face of climate change? Building on this approach then, we need to understand the climate variables that most influence coastal wetlands, a topic that our speakers will cover today during today's session. There should be no doubt that climate change is impacting the Great Lakes. We see this in warming air and water temperatures, frequent and extreme storm events that result in runoff and plumes of sediment and pollutants into surface waters, record-breaking high and low lake levels in the span of just a few short years, decreasing trends in ice cover that otherwise protect shorelines. And these are just some signs of what may come. If climate change continues on its current path, some of our Great Lakes could see little to no ice cover. This could mean greater wave energy, more erosion of shorelines and wetlands, flooding, water quality issues, and possible maladaptive actions such as even more shoreline hardening and other forms of alterations, sometimes in the wrong place. These changes in climate will likely persist and intensify over coming decades. The result could be even greater loss of coastal wetland habitat and the native species that they support, even in protected and diked coastal wetland systems. This brings us to ask, what's truly at stake for the Great Lakes? Why should we invest in coastal wetlands? What is it that we want to make more resilient? Put simply, wetlands are essential to the Great Lakes freshwater ecosystem. Where they exist, they form the first line of defense against erosion and the last line of defense against watershed pollutants. Hundreds of plant species are found within coastal wetlands, and this structure and diversity attracts over 155 species of birds, more than 30 different amphibians, and roughly 80 species of fishes of commercial and recreational importance. Wetlands also provide sustenance to local communities, mitigate climate change, and attract nature lovers. Wetlands also trap and cycle pollutants and help purify our water. A recent study out of the University of Waterloo found that based on costs for wastewater treatment facilities, Southern Ontario coastal marshes are the most effective wetland type at filtering sediments and removing phosphorus. Collectively, all types of wetlands provide about $4.2 billion in water purification services annually. Of course, the true value of wetlands is much higher when considering their other functions. Together, this translates to positive economic outcomes for the entire Great Lakes region. So why resilience and adaptation? Why is this an imperative? Despite the value of coastal wetlands that increasingly is recognized, their loss exceeds 90% in some parts of Southern Ontario relative to pre-settlement times. Many of the remaining wetlands are found within urbanized and agricultural settings where they must cope with stressors. Climate change compounds these existing stressors and poses a critical threat to biodiversity. Some of the largest wetlands are found within parks and protected area, yet it's questionable whether current protection efforts are sufficient for wetlands and wetland species to be climate resilient. For example, Point Pelee, Rondeau, and Long Point on the north shore of Lake Erie collectively protect roughly 90% of the remaining coastal wetlands on this lake. Yet you'll hear how these sandy geological landforms are at risk. Both development around the Great Lakes and climate change are taking a toll on the natural environment and reducing the amount of wetlands. Therefore, it's increasingly important for wetland resilience and adaptation. The changes to Hillman Marsh over the last 50 years serves as an example of how wetland or human actions compounded with climate change threaten coastal wetlands. On the left-hand side, you'll see that in the 70s, Hillman was sheltered from Lake Erie by a large sandy beach, and the wetland had diverse and abundant vegetation inside the barrier beach. By the 1980s, cottages and homes popped up here and elsewhere along the north shore of Lake Erie. To protect their assets, property owners armor the shoreline, and this has resulted in the disruption of natural processes such as erosion, sediment transport, and deposition of sand to nourish the beach. Fast forward to recent years, you can now see a massive breach of over 1/2 kilometer long from storms and recent high lake levels. Much of the wetland habitat has disappeared, and with it, the contribution to biodiversity and a natural solution to Lake Erie's nutrient problem. Across the Great Lakes, coastal wetlands are responding to climate change in ways that are difficult to understand and hard to predict. So to confront these unknowns, our team worked to achieve a number of goals and outcomes that we'll share with you over the next few days. We identified plausible climate trends and wetland vulnerabilities. We developed a suite of key adaptation strategies and measures with your input, of course, and we engaged broadly to improve the awareness of our study of what's at risk, the best approaches for adaptation. This wetland series adds to our engagement efforts. The ultimate goal, of course, as put forward by many of you, is to work together to ensure coastal wetlands are resilient. Credit for seeing this project through to its end goes to the scientists, modelers, field staff, and coordinators from 4 branches within Environment and Climate Change Canada. Over the next couple of webinar sessions, you'll hear from each of our project leads, our modelers, our scientists, and wetland biologists from each branch within the department shown on the screen here. I'd like to acknowledge the perseverance and the high quality work despite logistical challenges and trying times throughout COVID. I'm sure that most of you can appreciate this. We also thank you for your interest, your support, and your participation. This project began in 2016 with initial discussions with partners and organizations who encouraged us to examine climate vulnerability. We have landowners to thank for providing access to wetlands during 2 years of field surveys. We have the province, universities, and consultants to thank for spatial data, literature reviews, analyses, and insights into local wetlands. Thank you for your support at our small and large workshops and through questionnaires, our interviews, our focus group discussions, expert reviews, etc. We set out to ensure that wetland managers, scientists, and conservation practitioners were engaged in as many of your interests considered as possible. Recall that we selected a number of Canadian study sites from across the Great Lakes. We would have liked to have worked at more sites, of course, but that just wasn't practical given the large number of wetlands within the Great Lakes Basin, the complexity and cost of modeling, and of course, COVID. In the end, we were able to assess wetland vulnerability at 20 coastal wetland sites shown on this map. These wetlands can act as surrogates for wetlands of similar type and landscape influence, as we included different hydrogeomorphic wetlands, sites found within a gradient of land cover and land use intensity, wetlands on private land, on public lands, and wetlands within provincial and national parks and national wildlife management areas. 3 sites of cultural significance were located on First Nations lands, as indicated by the round black circles on this slide. We set out to examine coastal wetland resilience through first understanding vulnerability. In this first of its kind study for the Great Lakes, we deconstructed vulnerability into its key components. Potential impact, circled in red on this slide, was determined by integrating new climate and lake level projections into a coastal wetland response model. The model outputs were then used to determine wetland sensitivity by predicting changes in total wetland area, plant community diversity, volume of submerged aquatic vegetation, and wetland structure. The other component was adaptive capacity, or the ability of a coastal wetland to cope with climate impacts given its current conditions and landscape influences. This was assessed based on the landscape and wetland condition, the ability of wetlands to migrate under lake level changes, and the degree of protection within and around coastal wetlands. You'll learn about each of these components and how they are combined to determine overall vulnerability in tomorrow's session. There are a few considerations to keep in mind as we progress throughout this webinar series. We all know that there's uncertainties associated with the modeling. Something as complex as climate and lake levels and ecosystem response modeling is quite challenging. Our results are based on best available science, and this science will continue to evolve, of course. Our results should be regarded as trends and not predictions. The future climate, lake levels, and impacts will ultimately depend on greenhouse gas mitigation and adaptation. Nonetheless, the models used in this study are powerful tools and provide insight into management needs. Together, they can serve as foundational information for wetland adaptation. So with that introduction, our team thanks you for joining us for this first webinar session. We really hope that you enjoy the session, learn a lot, and appreciate the extraordinary amount of work that went into it. And with that, back to you, Sharon.
That's wonderful. Thank you for the great presentation and overview, Greg. Next, we will hear from Frank. Frank, please go ahead and share your screen while I provide a brief introduction. Dr. Frank Seglenieks is a water resources engineer with the National Hydrological Service of Canada within Environment and Climate Change Canada. Frank's research interests are in hydrological modeling of the Great Lakes for the past, present, and future, and his current position follows his time in the Civil Engineering Department of the University of Waterloo, where he worked as a research scientist and completed his PhD in water resources engineering. Frank, I see that you're all good to go. Your presentation slides look great, so the floor is all yours.
Thank you, Sharon. And unlike Greg's talk, which, of course, the title is Wetland Resilience, this talk is going to have nothing to do with wetlands, because this is kind of the base talk about what we can expect in the future as far as the hydroclimate goes of the Great Lakes. Myself and my fellow authors, who you can see on the screen there, are all water resources engineers, and we are part of Environment and Climate Change Canada. In particular, we're in a group called the National Hydrological Service. So what we have here is an outline of the talk. As with all these talks in this whole series, there's been, again, 5 years worth of work. So this is just going to be a very brief summary, and we're going to just try to hit the high points. I'm going to start it with the take-home messages. I used to leave them till the end. I've read different things that say, yeah, best to start out with them. Get cut to the chase, say, this is what you should take home from this talk. And then we'll get into the background and kind of the reasons why and how we got to those take home messages. So starting out, right here it is, boom, take home message number one. So we've seen trends in temperature and precip and evaporation already over the past decade. So the one take-home message is that the trends that we've seen in the past, all these projections of climate change are just projecting them to continue on into the future. So, people might think that climate change is a radical idea about, how the world's going to change. Well, in my opinion, it would be even more radical to say that, well, the trends that we've seen in the past decades are just miraculously going to stop and maybe reverse. What we're seeing is that those trends that we've seen, they're just going to continue. When we look at lake levels, we see that there's going to be, although a slight rise in the average of the lake levels, the more important thing to remember is that there's going to be more extremes in these lake levels, both low and high. So on both ends, we're going to see those under a changing climate. And so this graph shows kind of Lake Superior, what we've seen in the annual lake levels in the past, 50 years and 70 years, and where we see to go in the future. There's going to be more graphs like this in the future, so I'll explain more about what the different lines mean. The third one is very important, kind of goes on what Greg said. So although these studies all say that yes, we have the potential for higher lake levels, it's not a certainty. So what I've tried to show in here is like, I can imagine lottery balls and those big lottery balls when it's Lotto 649 and all those kind of things. So you have those lottery balls. So on the current climate on the left-hand side, you see that there's a bunch of green balls. Let's consider those are kind of the average, something in the average range of, let's just say, lake levels, but this can really be any hydroclimatic variable. And the red ball there is a more extreme, whether it's high or low. So you see under current climate, we can go through there, and then every year we're just picking a ball out of that lottery machine. And, we might go 10 years and not see a red ball, and then boom, maybe it'll pop up. Maybe it'll pop up twice in a row. Maybe it'll pop up 3 times in 5 years. That's kind of the way the weather system works. But you have a certain kind of probability of that happening. Now you move on to the next one. Well, let's say we change the global mean temperature by 1.5 degrees Celsius, which has come up in the news a lot. Well, now we're throwing another red ball in there. So there's more of a chance. And then 2 degrees, you put in more balls, 2.5, you see even more red balls. But so you see that there's a higher possibility as you get to these higher changes in global mean temperature, but it's not a certainty. Even at that 2.5, if you just keep going, you could go for 50 years and still just keep picking out green balls. It's not necessarily that you're going to see these, but just that there's a higher chance of seeing these more extremes. The actual changes, the biggest variable is how society acts. So just grab some headlines from recent newspapers. So, 1.5 degrees, 1.5 goals on life support, 2.0, 1.5. So these are all things we've heard in the news. So what's going to shape what we actually see in the future? This is going to be the main component, how society reacts to climate change and whether or not we can limit these changes in global mean temperature. And of course, there's uncertainty of any of these future climate studies. Again, as Greg said, we're based on the current state of the climate science. And just a couple of headlines there, like CMIP6, improved simulations of sea surface salinity, and then new climate models suggest faster melting of the Greenland ice sheet. So as new models come up, new data comes up, we're just going to be, looking and re-examining kind of the science. But what we're showing today is sort of the best that we can do right at this moment. So those are the take-home messages. Now, how did we get there? We'll do some background. So nobody's talking about this. So we're talking about climate change. You're talking about the IPCC. They do these things called assessment reports. As it turns out, the IPCC just did they released a report today about the CMIP6 results. So they do, as far as the what is going to change, they have these coupled model intercomparison projects called CMIP. So there was one for the assessment report 4 in 2006, 5, 2014, AR6, which is now just coming out. It came out a little bit earlier this year and data is starting to come out. So this study, we used what was called CMIP 5. that was originally released in 2014. You might ask, well, it's 2022. Why are you using data from 2014? Well, we'll see in a couple slides some of the reasons, but one of the important reasons, as Greg said, we started this about 5 years ago, 2017. So of course, when we started this, that was the data we have. We couldn't fast forward and get the data from 2022. But we're already looking at, of course, getting data from CMIP 6 and seeing how it looks at the future. So, and the other reason that we can't just use the data that's coming out now is that what comes out first are called the GCMs, global circulation models. So they typically have resolutions 150 to 200 kilometers. And you can see in the bottom left diagram there that what that means is that even as the lakes as big as the Great Lakes, some of the biggest in the world, you can't see them. You can't see them at that resolution. So what we have to do is a process called downscaling. And for that, we use what are called regional climate models, or RCMs, and they have higher resolution, anywhere from 25 to 50. They might even be getting even finer than that. So the important thing is that when you do that, on the right-hand side, you can actually see now, we actually can get the lakes. We can actually resolve the lakes. And for something like the Great Lakes, because there's such a large area compared to the watersheds, it's very important to actually see the lakes and have some kind of lake model for them. So if we close up, get closer, this is one RCM. It uses a resolution of 0.22 degrees, which is about 25 kilometers. And you can see the squares there that, yes, you can actually get some squares that are actually part of the lake. So we're at a resolution where now we can actually consider the lakes as actual entities. And then in this talk, we talk about one way of looking at the future is to divide it up into different time slices. We usually refer to a 2050 time slice, 2080 time slice. Some people talk about it mid-century, late century. It's all about the same. And then what we looked at were different carbon sequences. So as part of CMIP 5, which actually has changed in CMIP 6, but back in CMIP 5, we had different RCPs. And you can see the RCPs went all the way from 2.6 to 8.5. Won't get into the details of that, but in general, I would say most people agreed that RCP 4.5 was kind of the current state of the world with some mitigation of carbon emissions in the future. And our 8.5 was kind of business as usual. It goes very high. And you can just say the one takeaway from this is that you can see that the 8.5, which is the red line, it's in the mid-century around 2050. It's not that far off of 4.5, but when you get into the late century, you really see that it takes off from the other one. And so, yes, we see some more extremes with that, as we'll show in the future. I won't go into bias adjustment. This isn't a talk about bias adjustment. It could be a whole hour on it, but there's a in-depth reason of why we need to do it. We used a very robust technique that's been well established by Alex Cannon, also of Environment and Climate Change Canada. So just give a reference there. People can look at it if they want to. So splitting this up into two, we're talking about hydroclimate changes, the hydroclimate variables, first overland, and then the variables we needed to get lake levels. So overland, we can just look at something like this. Left-hand side, you see the trends in the current climate, again, going back to 1950, and the variability of the different models. And then on the right-hand side, you see the red line is the average of the models when you get it RCP 8.5, blue line, RCP 4.5. You can see that the red and blue lines are relatively similar, kind of in that mid-century, but then it's at the end of the century where the RCP 8.5 really starts to take off. So that's one way of looking at the data. You can also look at it kind of spatially, how the changes are over different parts of the basin. And then you can look at this one, which is kind of, I think, a good summary if you kind of look at it long enough and think about it. So what you see here in the bottom, very right, you see the changes in the annual temperature. And so there's 4 different bars there. The first 2 bars are the mid-century changes. The third and the fourth bar are also the end-century changes for RCP 8.5 and 4.5. And what you can get from that is that, again, the RCP 4.5 mid and late century and RCP 8.5 are all actually pretty similar. It's the 8.5 that really seems to go crazy in the last part. And you can also see that for temperature, the changes are more, you see more of them when you split it up, not just the annual, but looking at the seasons, winter to autumn, but then you can look at the individual months. So more of the temperature change you see is more happening in January and February. Then skipping the other graphs, if we just go to precipitation, you can see that the bottom right, yes, precipitation is forecasted to increase, but when you look at it throughout the year, it's definitely not the same over the whole year. So you can see that most of the increase actually happens in the winter time and early spring, and in the summertime, depending on where you are in the basin, you can actually see less precipitation in August, and definitely lower in those summer periods. Then we get in what's called snow water equivalent. This is just a way to measure how much snow there is on the ground. This is change in snow water equivalent, just basically negative. You can see that there's just a lot less snow going out there. Partly, I mean, it's a combination of temperatures and more rain on snow events. Then we get into evapotranspiration over the land. And again, you can just see that there's an increase in evapotranspiration. And then this results in changes in runoff. And as you can see, the differences in the precipitation throughout the year, if you look at the left-hand side, this is where you really start to see it. You see that in the and this is looking at different lakes, of course, Superior down to Ontario. So it depends on which lake you're in, but you can see there's a lot less change in a lot of the year, in the kind of the center part of the year, but a lot more runoff happening both in the winter time and kind of the early spring. So that's really where the difference is. You get more than just looking at the annual numbers. So now jumping to lake levels. So what we had to do is we took the RCM data, put it through what's called the Coordinated Great Lakes and Routing Model, and that gives us the different range in water level predictions. The routing and regulation model, as its name, takes into account the regulation of some of the lakes, like Superior and Lake Ontario, and gives you those projections. What the model needs as an input is something called net basin supply. So that's kind of the measure of the local water supplies coming into the lake. Two ways to compute it: component and residual. Component is the first way. This way we need the sum of the precipitation and runoff coming into the lakes minus the evaporation. And so we need values for the entire lake, and it's tough to get this data. So the historical record we get from the Great Lakes Environmental Research Laboratory, GLERL, a NOAA research laboratory in Ann Arbor, Michigan, and that goes back to 1950. So cutting to the chase on this one, again, on the left-hand side, you see what the GLERL hydromet database had as precipitation. This is for Lake Michigan Huron. And then on the right, as we saw before, there's the red line, which is the average of all the RCP 8.5s, blue line, RCP 4.5. And then just the spaghetti graph just shows you the variability. So you can see that most of it is still kind of in that average range, but you start to see some extremes as you go, especially further on into the century. And the important thing also is that, the runoff, the precipitation is forecasted to increase. Runoff, somewhat because it's also balanced by the changes in evapotranspiration. You see that it's not quite increasing as much. And then evaporation also increasing, and same kind of idea. And you put all that together and you get what's called the component net supply, net basin supply. And as you can see here, again, what you're seeing is that although precipitation is increasing, evaporation is also increasing. So they're offsetting when you're talking about the net basin supply, because you subtract off the evaporation. So you can see there isn't quite as big of a change when you talk about net basin supply, but there's still a bit of a change when you get to the later part of the century. And of course, you see some of those more extremes. And then there's a different way of calculating the net basin supply called the residual net basin supply. So this uses the change in water level and the amount of inflow and outflow from the lakes to calculate this net basin supply. We have a longer record. We have this going back to 1918. And one good thing, these are totally different ways of calculating the net basin supply, but we got actually quite similar results when we look at the residual net basin supply. So again, gradual increase, especially with the RCP 8.5, but you'd expect that with the more extreme carbon emissions. But you see that it's generally, average is like a lot of that meaty part is the same, but you start to see these higher and lower extremes. So as far as lake levels go, so we use the NBS to calculate the lake levels. Model calculates the flow, and the important thing is that this model was designed for the current weather conditions, current climate conditions. Now, on some of these more extreme future climate scenarios, we get inflows of net basin supply that, maybe some of these model assumptions are going to be violated in some of these high flow simulations. So like, for instance, there's no maximum flow in these connecting channels, whereas eventually the Detroit River, for instance, would hit its banks and it would spill out onto the floodplain. So that really isn't part of this model, because it always assumes that everything is within these connecting channels. So this is why we also have to look at, when we look at the future, have like a bit of suspicion as to whether these more extremes, if these lake levels are actually going to be seen. And then this is just a redone of that other graph about the extreme levels and more increase of seeing the increased chance of seeing them in the future, but not necessarily 100% certainty. So just going to end off here with some water level graphs, which is what people want to see. So this is for Lake Superior. Once again, all of these are going to have the same kind of trend. Obviously, the 8.5 has got more of the spaghetti plot extreme values, and just a general increase in the average levels of the lake levels going into the future. But it's really those extremes. And also you'll notice that there's extremes highs, but there's also extreme lows. So we can't just concentrate on the highs. And then we get into Michigan Huron, which this is actually the same scale as that other graph I just showed. All these graphs are the same scale, but just because of their the natural variability of Lake Michigan Huron, it actually has a higher variability, a higher range of lake levels. So you can see that clearly in this graph. And you can also see there are some extreme scenarios, like a couple of model runs there. This is RCP 8.5. This is well into the future. So it's best not to concentrate and recognize that these are very extreme cases where those happen. Going on to Lake Erie, same kind of thing. And Lake Ontario. Again, Lake Ontario is a different kind of beast because it does have a regulation plan. So then there's a question of what would happen with the regulation plan if we saw years and years of really high inflows into Lake Ontario. So would the plan be changed? Would there be deviations? So you also have to consider that. So in my opinion, it's important not to focus on these extreme levels that we see in some of the projections, but more concentrate on the what we call the 5% or 1% return periods. The details are going to be in the full report as well. We've got a couple of journal articles that are related to this as well that are currently in review and hopefully be coming out soon. So look for those as well. But so that's the important thing. There's more context in the reports and it shows you more. This is a 15-minute summary of what we have. So going back to the key findings, my last slide, just reiterating those take-home messages, general patterns of what we've seen in the hydroclimate in the past few decades. We see those continuing. Levels of Great Lakes, higher variability, more extreme highs and extreme lows. Got to remember they're both sides. That the higher emission scenarios obviously see more of these extreme levels, and the actual changes are going to depend on what society does, how close we stick to the 1.5 degrees C of the Paris Climate Accord. I mean, 2 was the official goal. There was a secondary goal of 1.5. We'll see how it all goes. And yeah, we're using the best science as we can, and we'll be, looking at how these same variables look under CMIP 6. So that's all, Sharon.
That's wonderful. Thank you so much for the great presentation, Frank. Lots of great information to digest. I'm sure there's lots of questions from the audience, and we've already received a few great ones in the Q&A. So please continue to input your questions in the Q&A box. We do have some time for questions before the break. So one question that the audience might be wondering is, Frank, why in the short term does the projections under RCP 4.5, the intermediate scenario, seem to be higher than the RCP 8.5, the worst case scenario, and only around the middle of the century does RCP 8.5 overtake RCP 4.5?
Well, I don't know if you're referring to just the slope of that graph and where they intersect. So, I mean, it's a trend line graph. We kind of show that they are actually the two emission scenarios are relatively similar for that mid-century part, and whether one is above the other, like 8.5 or 4.5 might be higher than 8.5. It's just the way that randomness and statistics work. So we're taking the average of a whole bunch of numbers that are bouncing around. So So we'd have to look at specifically which portion you were talking about, because I showed a lot of graphs there. But you know, in general, we see that the 8.5 certainly deviates more at the end of the century. So so inconclusive, but just that randomness that we see. I'll put it to that.
Thanks, Frank. And we have a question from Kevin. Kevin did note that you answered his question in your presentation, but just to tease it apart a little bit more, I think Kevin is wondering if you are concerned about any of the projected water levels in any of the Great Lakes Basin.
Concerned, yes, always concerned about you know, whether or not there'll be high water levels. There were high water levels in Lake Ontario in 2017 and 2019, which caused a lot of damage and headaches for a lot of people. So certainly, I think concern, and then saying, okay, what can we do about it? So there's a whole adaptive management part of this conversation to say, okay, these are levels we've seen in the past. This is maybe where we're going to go to the future. Let's use this information, this concern we have about higher water levels, and try to actually make changes into the way that we manage, construct things in the future. So I'm always concerned when we predict that there's going to be higher water levels, but I think it's a good message to work for the future and try to make it better and be more resilient and adaptable to these future water changes.
That's great. Thanks, Frank. And two more questions before we head into our 5-minute break. David is wondering to what extent Canada and the US are coordinating or communicating some of these climate change and lake level modeling efforts, as USACE, NOAA, and USGS are currently undertaking a similar effort on the US side of the Great Lakes.
Oh, well, we interact quite a bit. We are on various committees. I mentioned the Great Lakes Adaptive Management Committee, which might come up in some other webinars later on in the week. And there's also something called the Coordinating Committee. So we work very much with all those agencies, US Army Corps, NOAA, and USGS. And so we're always sharing information and getting them to review our stuff. Literally, people from NOAA and US Army Corps have reviewed this things that I have done. So we are always aware of the other side and what they're doing, and we try to interact as much as we can.
Wonderful. So glad that the coordination and collaboration is taking place. And our last question before the break is from Mary. Did you consider St. Clair River conveyance change outside of elevation change in your model projections?
At the moment, we do not. So that is, again, when I talked about the model, the Great Lakes Coordinated Regulation and Routing Model. When I talk about that and I talk about the assumptions made, one of the assumptions is that the conveyance doesn't change even as you go into the future. If you get higher flows, maybe that is going to change the conveyance. You're going to get more erosion. So these are all things that a more sophisticated modeler might look at, but at the moment we just use the model as is, use the assumptions, which is in this case no change in the conveyance as is. So this is something we're going to be looking at in the future.
Wonderful. Thanks, Frank. And thank you everyone for the questions. Please keep your questions coming as we move on to our presentations later this afternoon. We will invite Frank back for our panel discussion at the end of the webinar. So please continue to keep your questions coming. And let's take a 5-minute health break to refresh before our last set of presentations. And we are back. In the next hour or so, we will hear from Marianne and her team. I will now invite Marianne to share her screen while I provide a brief introduction. Dr. Marianne Bachand is a project coordinator in eco-hydraulic modeling within the hydrodynamic and eco-hydraulic section of the Meteorological Service of Canada. Marianne obtained her PhD in plant biology in 2013 and went on from Laval University and moved on to focus on eco-hydraulic modeling for her postdoc. She has been in her current role since 2016 and has developed several habitat and wetland models for water bodies spanning the Canada-US border. Welcome, Marianne, and thank you to you and your team for joining us today.
Good afternoon, everybody. I'm glad to be with you this afternoon. So the hydrodynamic and eco-hydraulic section is really enthusiastic today to present to you the results of a 5 years effort to evaluate the response of Great Lakes wetlands to projected climate change. I am Marianne Bachand, and I'm here today with three of my colleagues for this presentation, but I just want to highlight that 4 persons is not enough to develop what will be presented to you today. You have the names here of the other members of our team, and I want to underline their tremendous works during this project. So today we will look at the potential impact of climate change on the distribution of large wetland class, such as submerged aquatic vegetation, emergent marshes present on the front of that picture, wet meadows that we can see in the back of the picture, and shrubby and forested swamp that you can imagine really far in the picture. So to do so, several models are needed to allow to link the physics, the topography, and the vegetation. In our section, we use an integrative approach called the Coastal Wetland Response Model, as known as the CWRM. The CWRM is a spatio-temporal data layers, so observe and simulate data collection. Today, we will explain 3 key components of the CWRM and show you how we evaluate the impact of climate change on wetland classes with this tool. It is not the first time that we use an integrative tool such as the CWRM at the hydrodynamic and eco-hydraulic section. Similar tools have been developed in various water bodies in Canada and also in the United States, and are used to evaluate the impact of water level management or climate change on ecosystem, but also on socio-economic component of several basins. The modeling effort of the CWRM is across 20 sites in the Great Lake. Through the presentation, we will show you modeling results for most of the sites. If one site is not presented, just know that we have physical and wetlands model for all of those 20 sites available. Sites were selected for their hydrogeomorphological type, status, local or indigenous interests, but also according to data availability. The final product of the CWRM is a regular grid covering with a node at every 10 meters the area of interest of the 20 selected wetland sites. On the nodes, it's possible to calculate all the physical variables at a quarter-month step. It's mostly a week step, and the wetland class for a year for several time series. The CWRM includes 3 time series. The first one is the historical time series. It goes from 1980 to 2018. It's what we can call the time series of observation or measurement. We use that time series to calibrate and validate the different models. It helps us to answer the question, do we represent well that what was actually observed? In our words, it's what we call the states of reference. Okay, but to evaluate the possible impact of climate change, we use 2 other time series. Those time series are simulated. They are used to compare what happened in the simulated recent past with the simulated future, according with a climate change scenario. The recent past is the baseline, and the change or variation in wetland area or wetland class distribution during the future period is what will indicate us the impact of climate change. For now, the CWRM includes 1 carbon emission scenario called RCP 4.5. It's a moderate carbon emission scenario, and it represents a weak mitigation of our CO2 emission in the future. The projected increase of the temperature with this scenario is around 3.3 degrees. The RCP has been run with different global circulation models. Due to time calculation, only 2 simulations were done in the CWRM. The lower bound called CAN ESM2 and the upper bound called GFLD ESM2M have been returned to cover the range of possible future according to wetland distribution. Okay, so now back to our CWRM representation. The first step of the CWRM model it's to scale down the weather data from the global atmospheric model to the hydrodynamic of the 10 by 10 CWRM grid. I will let Dr. Rémi Gosselin guide you through this effort.
Okay, thank you, Marianne. Can you everyone hear me? Good. All right.
Yes,
So
Rémi.
yeah, if you go to the next slide. So yeah, so the first part of the physical process is to go from the global model down to the average lake levels and to instantaneous winds for the hydrodynamic model. So this process was presented by Frank in the previous presentation. The only thing we add to that is that we also extract the wind because it has a great effect on the local water levels around the lakes. So if you go to the next slide. Here I present the lake levels for all four lakes in the CWRM, both under the upper and the lower bound scenario of RCP 4.5 that Marianne talked about earlier. And you can see that under the lower bound, lake levels are mostly remaining about the same that they are today, or slightly lower. Whereas with the upper bound, lake levels tend to go higher, but with also higher year-to-year variation. So if you go to the next slide. So the first main physical process that we take into account is the short-term and the long-term effect of the wind. When wind blows through a body of water, it creates a slope on the lake, and so it's lower where the wind comes from and higher where it goes. And this is called a setup. And when the wind stops, the lake eventually goes back to an equilibrium, but it oscillates between it oscillates around the mean lake level. So this is called sesh. And you can see that both phenomena create water level oscillations, sometimes in excess of 50 centimeters. So these oscillations, this wind effect has a great impact on water level, especially in wetland sites around the lakes. The second physical process linked to the wind is the wave generation. So on a body of water, you have three different zones. You have the deep waters where the waves are generated. Then as you go closer to the shore, you have shallower waters where the effect of the flow starts to have an effect on the waves and changes the velocities and the height of the waves. And finally, you have the surf zone on the shore where the waves break with most velocities and friction at the bottom. So if you go to the next slide. So once we have the mean lake levels from Frank and the winds, we can go to the second part of the process, that is a hydrodynamic modeling. So it solves the fluid dynamics equation across the whole lake, and it allows us to translate the mean water levels from one value to a map of water level across the area. And it uses bathymetric data. It uses the different tributary discharges that we can derive from the net basin supplies, and it also needs water level boundary conditions. For example, in the case of Lake St. Clair, we use the water levels of Lake Huron and Lake Erie to force the model, if you want. And we also need additional forcing, for example, the wind time series everywhere on the mesh. And what we get for this from these kinds of models is the water level and the flow velocities at each mesh node. So if you go to the next slide, Marianne. Here you have an example of the computational model for Lake St. Clair. So basically, it's a large assortment of triangular elements, and each triangular element is composed of 6 nodes. And you can see on the right the various zoom levels on the mesh. So in the middle of the lake, elements are about 750 meters long. But if you go closer to the shores or in the connecting channels or the river, it goes down to elements are down to a few meters. And on the left of the slide here, you can see the bathymetric data for that particular lake. So next slide, yes. So this is just to show you how the process work, how we create the time series. And so at each time step, we evaluate the boundary conditions. So for example, here the water level at Lake Huron upstream and at Lake Erie downstream. We also know the instantaneous wind map all across the grid. And with this information and the data from the previous time step, we can run our calibrated lake model and compute the new hydrodynamic conditions at this time step. And we build the time series like that. Okay, so here is just to give you an example of the sort of precision we can achieve with such modeling. So these are the calibration results for Lake St. Clair. So in other words, it's just the difference between the observations and what the model gives in terms of water levels. And so you can see that there is a slight month-to-month variation in terms of precision, especially in the spring, because our model does not have ice modeling. But overall, the error is 3 to 5 centimeters. And if you go to the next slide, in this table, you have a summary of the different hydrodynamic models for each lake. So for the upper central sewers, that is a separate model. You have for Lake Ontario, Lake Erie, Lake St. Clair, and Lake Huron. So you can see the size of the different meshes varies greatly. For example, Lake Huron, it's 1.8 million nodes compared to 300,000 in Lake Erie. But the overall error at the end is in the same range between 3 and 5 centimeters, which is quite good for hydrodynamic model. So the third part of the physical process is wave modeling. So it's a completely different approach. It uses a nested approach with 2 different models and 4 different grid resolutions to go from the global deep water, if you want, wave generation, and then go closer and closer to the wetland sites. So the first model is called Wave Watch 3. So it uses a 500 meters grid across the whole lakes. And the second one is Swan. That uses grid resolution between 150 and 50 and 20 meters. So if you go to the next slide. So here, for example, you can see the different grids used for Lindy Creek in Lake Ontario. The blue, green, and red areas are 3 Swan grids. So we first calculate the whole lake, then we switch to the blue Swan grid, and then we use the result for the blue one to feed the green one, and then the red one. On the right, you can see examples of results that we can obtain with wave modeling. So we have the wave exposure at Rondoboy. So basically the orbital velocity of the wave statistics on a year, if you want. So you can see that the beaches around the sites are the most affected by waves, but there's also wave velocity in the inside of the site where there is plant growth, so there is an impact of wave in the site. So if you go to the next slide. So all of this physical modeling, so as the hydrodynamics and the wave modeling, has only one goal, is to generate time series of various physical variables for each point or each node of the CWM grid, and that will be used by the wetland succession model. So here you have an example of the variation of a few of these variables for the lower and the upper bound scenarios when you compare the recent past or the baseline and the future period. And as you can see, climate change does have an effect across all sites, but it's not the same. It's not the same effect in Lake Ontario that it is in Lake Huron. So you can't really have a broad conclusion just from this. If you go to the next slide. So here we have a more complete list of the relevant physical variables that will be used by the wetland modeling. So just go from statistics on water depth to maximum flow velocities, different time periods or cycle lengths, wavelet power or the energy of the oscillations if you want, or statistics on whether a node is wet or dry during a quarter month period, etc. So now I will show you just a few maps of the differences of a few variables between the lower and the upper band scenarios. If you go to the next slide. So here you have the evolution of the partially flooded area in Airport Creek in Lake Ontario. Under the lower band scenario, Lake Ontario lake level is mostly the same as it is today. So there's not a lot of projected change between the baseline and the future period. However, with the upper bound scenario, lake levels are projected to increase. So there's a much larger portion of the site that is being at least partially flooded. Okay, so this is Lindy Creek, also in Lake Ontario, and you have basically two maps on the left that presents the mean water level depth and how it increases under the upper band scenario. And well, because the lake goes higher, basically what it does is migrate the site inland. And this also have an effect on the energy of the oscillation. So because the center part of the site sees deeper waters, the energy associated with that is slightly lower, whereas the energy on the inland parts of the site sees more energy. And finally, the last example. Next slide. So here we can see the evolution of the mean cycle duration for Rondo Bay in Lake Erie. And so in other words, it's the number of days where the grid nodes is subjected to lake levels fluctuations. Under the lower band scenario, cycle tends to increase in the eastern part of the site because mean lake level tends to go down. Whereas in the upper band scenario, the eastern part of the site would not undergo longer cycle because it would be flooded more often, and the inland part of the site would. So once again, it's all linked to the mean lake level that is higher under the upper band scenario. So next slide. So because it's already a dense presentation, we have a 5 minute question period before we switch to the wetland modeling. So if you have any question regarding the physical modeling, you can go ahead.
Thanks, Rémi and Marianne, for the great presentation. We look forward to hearing from Antoine and Dominic following our quick Q&A as well. So please continue to type your questions in the Q&A box if you have any for Rémi and Marianne. A question for both of you, Marianne and Rémi, is whether there are plans to model coastal wetland responses under RCP 8.5 as well as part of future work?
I can answer that, Marianne, if you want. Yes, yeah, we developed the. It's not only the results; it's also the method that was part of the product. So yes, we could eventually run some RCP 8.5 time series. We actually had a one-time series at the beginning, but there was some problem with Lake Ontario, especially. So we didn't run that, and it takes quite a long time to run, but eventually, yes, we will.
I'm sure it's very time consuming with the amount of data that you have integrated into the model. It's amazing. A question for Marianne, or unless Marianne, did you want to jump in on that question as well?
I think if we just want to summarize Rémi's answer, it's that it's possible, but it's not something you get in a week. But everything is ready to run it.
Great, thanks, Marianne. A question for you, Marianne, as you mentioned that integrated ecosystem models have been used in other water bodies in Canada. What are some benefits and drawbacks of this modeling?
Oh, that's a PhD question. It's a really nice one. I think the one thing that we can learn from past RERM, Integrative Ecosystem Response Model, it's possible to have just few indices giving you answer on a really large, complex system. But everything that is simplified, let go of some information too. So it's like you have to find what I would call an equilibrium by both.
That's great. And I'm sure it is a balancing act in terms of the course and detail and scale as well. So our next question is about the wave modeling in particular. Is it possible to use the wave modeling to understand changes in erosion, not just water levels?
Yeah, eventually it could be used to evaluate erosion. The effect on the shore. It just requires a lot of post-processing to do that, and a lot of data to calibrate it also. So it's not straightforward, but it will be possible. Yeah.
But it's also possible with the wave model to just have a proxy of erosion. So where you have more wave energy, it's where you may have more erosion. So.
That's great. Very interesting. And we have one last question that we'll take before Antoine and Dominic's presentation. And I see some of the questions are relevant to Antoine and Dominic's presentation, so we'll save them at the end. So our last question is Mary's. So the future range projections for Georgian Bay are much greater. Do you plan on modeling impacts on shield wetlands as well?
I'm not sure what's the definition of shield wetlands, but I will imagine that it's an inland wetlands. Am I correct?
Let's take it as wetlands within the Canadian Shield, so perhaps more inland.
Okay, so I will answer that if there's a link to the water level, and if in one scenario the water level has an impact on that wetland, it's possible to apply the model. But if climate change, let's say, have an impact on that specific wetland regarding evapotranspiration, but is not directly linked to the water level of the lake, no, it's not possible to apply the CWRM right now.
That's great. And Mary, if we didn't answer your question properly, please do follow up with us in the Q&A or the chat. And with that, thank you again, Marianne and Remy, for the great presentation. We'll pass it back to Dominic and Antoine.
Okay, thank you, Sharon. So to see how the physical variables presented by my colleague Rémi may transpose on each selected wetland, we need to have an accurate representation of the bare earth elevation of all sites. To do so, we created 2-meter resolution digital elevation models, which cover the land and water interface of all the selected wetlands and their surroundings. That covers a total of more than 3,000 hectares, which is more than 7.5 million elevation values. And the main challenge of this task was to have elevation values that are as close to reality as possible. We can change slide. And this is not an easy task, since our primary topographic data source are aerial LiDAR surveys. And the LiDAR tends to create a positive elevation bias in densely vegetated areas, such as coastal wetlands. Imagine measuring the bare earth elevation in a highly vegetated cattail marsh, as we can see on the lower right image. The laser pulse of the LiDAR cannot penetrate the dense canopy and measure the bare earth elevation in those cases. So in our case, it was creating vertical measure errors of more than 50 centimeters on average over all sites. You can change slide. So it was clear that we needed to correct these errors. So we adopted the lean method, which was developed by Kevin Buffington from Oregon State University. It's a statistical correction model based on multispectral imagery characteristics and ground truth points. We applied this method, and by so we reduced vertical value error by more than 50%, giving an average root mean square error of 24 centimeters among all sites. And the positive elevation bias was eliminated with error distribution more centered towards zero. We can change slide. Another great challenge was to gather bathymetric values that cover the lacustrine part of all sites, since the LiDAR surveys can't measure elevation values underwater, since the laser pulse is mostly reflected on the water surface. And since there was not a unique bathymetric data set covering with precision such a large area, we needed to create a mosaic of several different data sets from various acquisition methods and with various precision and accuracy levels. So after several adjustments and correction, a unique bathymetric data set was created for each site and transposed on the rigorous grid with various interpolation methods such as ordinary gradient. Those data sets were then merged with the topographic data to create seamless DEM covering each site. So that process gave an accurate 3D representation of each wetland topography at a 2-meter resolution. We can see an example on the animation on the screen right now for Grand River Mouth in La Querrier. So this process covers all study sites, and we have an absolute median error of 16 centimeters when compared to 7,000 ground truth points. Normally, the animation is more fluent than that, but unfortunately, with so many attendants, I think it's lagging a little bit. So yeah, we have an absolute median error of 16 centimeters when we compare it to more than 7,000 ground truth points. And our error values are centered towards zero. So that means that the positive elevation bias was eliminated. And then from that, primary terrain attributes such as slopes, aspect, and curvature could be calculated at different resolution and used in further CWRM steps. We can change slide. Again, a small animation showing that one main usage of DEM is to show how water level variations may affect the wetland. As we can see on the animation here with the gray, which is water level rising, we can see how water level rise impact the wetland. We can change slide. And more particularly in the context of the study, it is quite useful to see how future water level may transpose on each wetland. Here we have the example of South Bay Marsh in Lake Ontario. So in the lower left, we see the mean water level under the recent past period, how it transposed on the wetland. And then on the right, on the upper part, we see the lower bound future scenario, and on the lower part, the upper bound future scenario. So we see, for instance, that under the upper bound future scenario, the mean water levels covers a bigger part of the wetland that it was doing under the recent past. And then we have the same example for Hog Bay and Lake Huron here. It's a bit more subtle, but we can see that towards the end of the bay, under the upper bound scenario, the mean water levels covers mostly all the portion with the wetland in that area. So that's how we calculated and got the accurate elevation values covering all the wetland sites in this study. Thank you. I'll leave you with Dominic to present the wetland class succession model.
Thank you, Antoine. Yes, so now I'm going to present the wetland modeling portion of the study. So how do we link the physical variables showed before for the various climate scenario to the wetland classes? So we have two steps. So there's the calibration during the historical period, and there's the prediction on climate change, comparing the recent past and the future. Can you change slide? Okay. So the wetland modeling includes several steps to link the physical variable to the wetland class observations. So we use different data. So the wetland observation from various sources. So we need the vegetation survey samples where we identify the species in the wetlands at the quadra scale. And we also use a remote sensing wetland classification at a much larger scale. And we link those observations with the physical variables and the terrain variables. So using a random forest model, this algorithm makes the relation between the variables and the wetland classes. And then we use another model, which is the succession algorithm, which modulates the transition of the wetland classes according to the different tolerance and resistance of those classes. Once we have calibrated those two models, it's an iterative process. Once we have a satisfactory models, we can predict the wetland, simulate the wetland for each site across the whole time period and on climate change or on the historical period. So the wetland class that are modeled go on a hydrocère gradient, elevation gradient from the wettest, from the lake to the upland forest. So we modeled the submerged aquatic vegetation, and then the emergent marshes, the wet meadow, and in some sites, in the lake area sites, we modeled the two classes of swamps, so the tree swamps and the shrubby swamps. And in the other lakes, we had a broad swamp classes because we did not have enough data to have both classes. So the random forest model is a supervised that is calibrated with the wetland observation as dependent variables and physical variable as predictor. It's calibrate and validate an ensemble of decision trees where each tree votes for a given class. And the majority of the vote is the class that is selected, or we also can have a probability for each class. This is not a black box model because it gives an estimate of the error, the strength, and the correlation and the variable importance for the global model, but also for each wetland classes. So here in this figure below, it's the global variable importance for the lake area model. The minimum water depth is the most important variable, followed by the slope and the curvature. We can see also that the mean water depth and the maximum water depth are also important predictors. And also interesting to see that the wave is very important to the model. And the three other variables are also important because they were selected in the model. Now I'll present you the succession algorithm. It's a very complicated model. It includes many different paths, possible path according to the random forest predictions or according to physical variable thresholds. So here I'm just going to show an example of if one year, like for example, year one, the class predicted at the point is open water, and on the second, the next year, the conditions are drier. It can become within 1 year submerged aquatic vegetation. Then the next year, if the conditions are still drier and the submerged aquatic vegetation is mostly dried out, it can go to emergent marsh. But at emergent marsh, this class has a resistance of, it's a class that can resist adverse conditions. So it will require at least 3 years of wet conditions to go back to SAV or open water, or 3 years of dry conditions to go to shrubby swamp or wet meadow. The other classes, wet meadow, shrubby swamp, tree swamp, they all have the same kind of mechanism, but with different thresholds. So yeah, I think that's going to be it. For more details on this, our report is very explicit. So here is the different validation scores for the models that we have developed. Most models have accuracy and kappa, accuracy higher than 70% and kappa higher than 60%, which is very good for wetland models. Here, it's an image that shows the CWRM simulation on the left side and the wetland observation on the right side by the Ecological Land Classification dataset in South Bay in 2008 in Lake Ontario. We can see that our predictions are pretty close to what is observed in reality, especially for the emergent marsh in this site. Here we have the same kind of image, but with a little animation in Rondeau Bay. So on the left side, it's the prediction, and on the right side, it's the observation. Our model reproduces very well what is observed, like this big emergent marsh area and the shrubby swamp and the upland. So we're pretty satisfied with the results in this site. So now this is an animation. On the left side, you have the water level and fluctuating, and on the right side, you have the wetland. So when the water level is higher, you have more open water, and when it goes down, you have more submerged aquatic vegetation in light blue. When it's stable toward the time, the other class like wet meadow and shrubby swamp will tend to increase. And with the high water level in 2017, anyway, we switched slide. Okay, so now with the high water level in Lake Erie, we can see that in this lake, the water level fluctuates way more, and the wetlands are way more fluctuating. With higher water levels, there's a lot of submerged aquatic vegetation, and when the water levels is lower and stable for a long period of time, there's more wet meadow and shrubby swamps. Yeah, and with the higher water levels, you see will be more open water and submerged aquatic vegetation. So now for the results, I will present the results in form of bar plots for the first slide for each lake. So in the first slide, we'll see the result for each site within a lake for both climate change scenarios. And then on the second slide, I'll present map results for one site or more. And the third slide will be the key findings for this lake. So here we present the relative change between the recent past and the future for each wetland classes. So it's the mean area in the recent past versus the mean area in the future period. We have the difference in terms of percentage for each site, and the higher figure, it's the lower bound scenario, and the lower figure is the upper bound scenario. So the response of each lake and sites are very site specific. It depends on the site. With the lower bound scenario, there's slight change in total wetland area. But there's some, we can see there's some increase in SAV, but it's not significant because there's a high variability in the future period. You can see there's a decrease in wet meadow, but it's relatively low. With the upper bound scenario, there's a high increase in submerged aquatic vegetation because the water level is increasing a lot in this lake in comparison to the lower bound. This caused in a loss of swamps in South Bay, Lindy Creek, and Jordan Station, and also a loss of wet meadow. And now we're going to see the result in Airport Creek. In this site, yeah, okay, it's all right. Okay, so Airport Creek is an open drowned river mouth. On the figure on the left side, you have the masked area, so that highlighted by white. It's areas that were not integrated in the model. So here, and with the lower bound scenario for SAV and so submerged aquatic vegetation and emergent marsh, there's an increase of both classes with the lower bound scenario. So with stable or slightly lower water levels. But with the upper bound scenario, there's a big increase of emergent marsh landward, and there's a landward migration. Sorry, for submerged aquatic vegetation, there's a big landward migration increase, and for emergent marsh, there's a landward migration of this class. We can switch slide. So the key findings in the upper St. Lawrence River and Lake Ontario are that the total wetland area is expected to remain stable or to increase with higher water levels. The submerged aquatic vegetation will increase under both scenarios at the expense of emergent marsh and wet meadow. And the upper bound scenario causes inland migration of wetland classes where swamps are reduced the most. So now we're going to present the result for Lake Erie. So in this site with the lower bound scenario, there's an increase in wetland area. And there's an increase in, you can see that in Selkirk Provincial Park, there's an high increase in the emergent marsh and swamps. And in Long Point, there's a high increase in emergent marsh and swamp also. And there's a decrease in submerged aquatic vegetation in Rondeau Bay and Fox Creek, and a high increase of wet meadow in Fox Creek. But with the upper bound scenario, what is important here is that a lot of there's a high reduction of wetlands in all sites, with swamp being resumed up to 60% in Grand River Mouth and 50% in Rondeau Bay. And in Long Point, the wet meadow suffers a lot by 60%, and also the submerged aquatic vegetation is reduced a lot in this site. Now we're going to focus on the results in Long Point. In this site with the lower bound scenario, there's slight change for emergent marshes, but we see that there's a lakeward migration of wet meadow for the lower bound scenario. Under the upper bound scenario, there's a slight change for emergent marshes, but there's a high decrease of wet meadow with the upper bound scenario. So for Lake Erie, the total area slightly increased with the lower bound scenario and a decrease with the upper bound scenario. The lower bound scenario slightly increased the emergent marsh, wet meadow, and swamp area and decreased the submerged aquatic vegetation area. And under the upper bound scenario, there's an inland migration and an important decrease of most wetland classes, with where swamp is the most affected. So here we present the results of Lake St. Clair and the Huron-Erie corridor. So for the lower bound scenario, there's a slight increase in the wetland area and a high increase of swamps, but it's important to say that there's not much swamp in those sites. So it's not a class that is very abundant in the recent past. For the upper bound scenario, there's a major decrease in wetland area and for all wetland classes in all three sites. Now we're going to focus on the results of Detroit Mart and Johnston Bay. Okay, we can switch slide. So for Johnston Bay, this site is a site that has a lot of diked areas and also agricultural crops that are masked from the results. And those dikes limit the wetland migration. So for the lower bound scenario, there's some changes in submerged aquatic vegetation, but like it's like it decreased in some places and increased in others. For the emergent marsh, slight change also, but where we see the major change are with the upper bound scenario. The submerged aquatic vegetation increase towards the landward, and the emergent marsh has no room to migrate, so it's mostly all eradicated. So there's a big, here we see where the big loss in wetlands is in this site. I will go to the Trois River Marsh. So this site is also a site that is highly modified by the humans. It's a site that a lot of the area is masked because of agricultural crops and residential houses. So for the lower bound scenario, there's a lakeward migration of emergent marsh, and there's also an increase in swamp because the water level are slightly lower. But with the upper bound scenario, there's a high decrease of emergent marsh. So mostly all the emergent marsh that was there is completely flooded and is replaced by other classes like submerged aquatic vegetation or open water. And under the upper bound scenario, there's not much swamp in the recent past, so there's slight changes for this class. Can we switch, please? So for the key findings in Lake St. Clair, with the lower bound scenario, there's a slight increase in the total wetland area. And with the upper bound scenario, there's a major decrease in total wetland area. The lower bound scenario causes a lakeward migration of wetlands and increase most wetland classes area. But with the upper bound scenario, the wetlands are forced to migrate, but they cannot migrate since those sites are located in highly human altered areas. So now we will present the results for Lake Huron. With the lower bound scenario, the changes are really small. In Hog Bay, Treasure Bay, and the Whiskey Harbor, we can expect some increase in wetland area, but in the other side, the total area is not expected to change. The slightly lower water level seems to favorize the swamps with the lower bound scenario. For the upper bound scenario, there's a decrease in wetland area for all sites, except the A Bay where there's no change. But this is not because there's no change in percentage of the relative area that there's no change in spatial. What happens is that the wetlands are able to migrate upland because most of those sites are located in a natural environment and there's room for wetland migration. But even if there's room for wetland migration, we still see some important loss, such as the emergent marsh that seems to suffer a lot in most sites, in the Baie du Doré, A Bay, Hog Bay, and Treasure Bay. The swamp class seem to be able to migrate in most sites, except in Whiskey Harbor, but this site has to be taken with a grain of salt because we had the study area does not cover an enough big area for wetland migration. So it's a bit of an outliers in this presentation. So now we're going to present the Baie du Doré result and the Treasure Bay mapping results. So for Baie du Doré, for emergent marsh and wet meadow, there's a lakeward migration of those class with the lower bound scenario. But with the upper bound scenario, both classes increase landward. So with higher water levels, there's room for the wetlands to migrate in this site. In Treasure Bay, we can see it's pretty much the same thing that happened. With the lower bound scenario, there's an increase of emergent marsh and swamps towards the lake. And with the upper bound scenario, there's an increase of emergent marsh and swamp towards the lands. So since those sites are located in mostly natural settings, slightly altered by the human and human land use, the wetland migration is possible. Can switch, please. So for the lower bound scenario, it's slightly increasing the total wetland area, whereas the upper bound scenario decreased the wetland area. With the lower bound scenario, the swamp is increased in most sites and slightly increased the other wetland classes, in exception of submerged aquatic vegetation. With the upper bound scenario, the emergent marsh is decreased and the wet meadow also decreased in most sites, but the swamp class seems to be able to migrate and to not suffer as much losses. So yeah, I think that's it for the wetland modeling. I'll pass the talk to Marianne.
So you saw that that slide a few times in the presentation. So in summary, you just learned how we use an integrative approach to link the physical component, going from the atmosphere to local component with the wetland class distribution of 20 wetland sites of the Great Lake, and evaluate the impact of one CO2 emission scenario. I will show you here a graphic. So you have a graph here with all the sites and the projected change in total wetland area on the y-axis. So in general, the total wetland area decreased more under the upper scenario than it increased under the lower scenario. So it is most likely that wetland in the Great Lake are at risk to decrease under a weak mitigation scenario in the future. So impact of climate change on wetland class distribution. It's difficult to identify a trend across all Great Lake, but the response of wetlands to climate change are more lake specific and sometimes even site specific. In general, in Lake Ontario, submerged aquatic vegetation area increases in the future in all sites for lower and upper bound when wet meadow and swamps areas decrease. In Lake Erie, in general, for the lower bound, the response are site specific. The extent of all wetland classes is reduced in the future for the upper bound scenarios. In Lake Erie and Erie-Huron corridor, the extent of all wetland classes slightly increase in the future for the lower bound, but decrease for the upper bound scenario. So that's the summary of the result regarding the climate change. But I also want to talk to you about the CWRM. The CWRM is not just for climate change scenario comparison, it's a collection of standalone product. So in the CWRM, we have hydrodynamic models of 4 water bodies. We have wave model for 13 wetlands. We have high resolution DEM of 26 wetlands. Why not 20? It's because at the beginning we have 26 sites, but to different time constraint, we have to reduce it to 20 wetlands. And I want to say that 2 of those 6 extra sites are in Lake Superior. So we are not forgetting you, Lake Superior. We have several physical variables calculated at the quarter mile time step for various time series. We have 2 models that look at invasive species, so one for cattail, one for Phragmites. And we have a georeference vegetation survey for 26 sites done in 2018 and 19 that was coordinated by the Canadian Wildlife Service. The CWRM is a wonderful tool and it's incredible, but it doesn't include everything. So not included yet in this effort is, for example, sediment transport and morphodynamics, nutrient supply, ice, if a new exotic species enter the system, toxic chemical exposure, the change in land use. So we include land use in the CWRM, but it's the actual land use, water clarity, and other component too. So the CWRM is not just a promising tool, it's also a useful tool right now. It's possible to add other sites in it. It's possible to analyze other climate change scenario. We can develop other kind of model, not just wetland model, but it can be used in a faunal habitat quality models. It can also be used for other purpose, such as evaluating management or conservation plans. And I just want to say that the result that was presented to you today, the wetland class distribution time series, are an input in the sensitivity analysis conducted by the Canadian Wildlife Service within the GLP project. Before we let you go on our answering question, I want to give you some fun facts about the CWRM. So it's a 5-year project, and we have 14 employees that were involved in that project, and we are from different perspectives. I'm a biologist, Rémi is an engineer, Antoine and Dominic are GIS expert. We also have geomorphologists in our team, mathematician, programmer, name it, we have it. The final grid of the CWRM, it's 2.3 million nodes. And you can imagine that to run those kind of model, it takes time. So I'll just give you an example. The wave modeling, it's take 3 months to compute one lake. We have a huge amount of data. Another example, the wetland modeling is 2 weeks of computing for one lake, and it took several months to develop. And our final report to go out, I expect by the end of the month and next month, is about 425 amazing pages with 210 figures. So every maps you saw today, we have it for all the 20 sites that were under study. So I thank you very much for your time. Here's the name of our people involved in our team. And I just want to say that we are presenting the invasive plant modeling this week, April 7th in the afternoon. So we will be presenting you a result from the cattail and Phragmites models. Thank you very much. I know it was a long presentation.
Thank you so much, Marianne, Antoine, Dominique, and Rémi for the excellent presentation. We had so many interesting questions inputted into the Q&A box. Please do keep them coming. So our first question is for clarification from Rob, is whether the CWRM results for future upper and lower bound scenarios are really based on comparing change over the historical period of the 1980s to 2010 to change over 2070 to 2100, and just wanted to confirm whether this is the case.
The answer to that is no. We compare the simulated recent past with the simulated future. The historical time series going from 1980 to 2018 was used to validate and calibrate the model. But to compare the impact of different climate change scenario, we simulate the recent past, 1980 to 2010, and we compare it and we look at the change in the future by the end of the century.
That's great. That's very helpful, Marianne. And a second part of Rob's question is really to help understand what the upper and lower bound means in terms of future water levels and waves. How likely are those going to be in the future?
It's quite hard to say whether one is more likely than to happen than the other, because it's only 2 scenarios in an ensemble of scenarios, and we only selected them because it's really the lower bound and the upper bound of the ensemble of scenarios. So it might be between the two. Yeah, it's quite hard to put a likelihood of occurrence on one or the other. It's not how it works. Yeah, you can see a slight grayish water levels time series, and so the upper one and the lower one are really really the bounds of what could happen in RCP 4.5.
Wonderful. Thanks, Remy and Marianne. So hopefully that clarifies your questions, Rob, but if not, please do follow up with us in the Q&A. So this is to the entire team, anyone who wants to take it. Did any aspects of the modeling results surprise you at all? Perhaps we'll start with Marianne. Any surprising results?
I think I'll keep my answer for the invasive plants model, but no, I was expecting a loss in the wetland area for more sites. I was expecting also maybe a more generous trend across the wetland class distribution. But since the wetlands in the Great Lake have different shapes, different dynamic, at the end, I'm not that surprised that we see almost sometimes even specific site response.
Interesting. Remy, did you want to go next?
No, not much to add on the physical part. No, we follow the results from Frank's analysis, so we know firsthand. We know how the water level we go, the mean water level we go. So no, not really. Nothing out of the ordinary on the physical part.
Great. And how about you, Antoine? Any surprising results?
I think it's quite interesting to see how the land use is limiting the upland migration of the wetlands. Which how much is it a factor to consider? We see a lot of sites where there's some wetland class decline, which is due to the incapacity of the wetland to migrate upland because of the land use.
That's great. And how about you, Dominic?
In some lake, there's like more variability in some classes, like in Lake Ontario, we see there's a high increase in submerged aquatic vegetation. That's something that surprised me a little bit. But overall, I think our model fits pretty well what we could have imagined. Like with the increase in water level, we imagined that the wetlands suffer. But yeah, also the invasive species presentation, I think it's very surprising, and you will see more results on the April 7th. Yeah, overall, I'm pretty satisfied with what you see.
Wonderful. That's great. Thanks, Dominic. And next question is recognizing that Marianne and the team, you've emphasized how lake specific the results are. Are there general patterns that you're seeing across similar types of wetlands across lakes? Do different types of wetlands respond better or worse than others to changing water levels and waves?
That's a good question. We didn't do like a statistical analysis, for example, for all open embayment or all river wetlands that we have, because we don't have enough site of each one to make those kind of analysis. But just, looking at the result, I was not able with Dominic to have a general trend for that either. But that's a really good question.
Great, thanks, Marianne. And we have a question from Andrew. Could you take this information to pinpoint the wetlands that are limited by ability to migrate in response to the water level scenarios? This would be great for determining if there are wetland priorities for restoration if possible.
Yes, we can do it, but I will also invite you to go at presentation in the tomorrow, because they also analysis of done by the WLSD that look at the possibility of wetlands to migrate. So I think you will be more satisfied from that study regarding your question.
Great, yes, and please do join us for the session tomorrow. We have a question from Jeff. He says, great research. Many Great Lakes coastal wetlands are controlled by barrier beach. Did your research find that many barrier beach marshes are at risk of future loss? If this isn't already apparent, examples include Hillman Marsh and Point Pelee, a marsh in Western Lake Erie.
Okay, so Jeff, this is a wonderful question. And it's where maybe you'd be sad of our work. It was not possible for her to include barrier beach in our effort for now. We need to model the stability of the barrier, and it's we need to put some times. We need to think about how we can model the opening and the closing of the barrier beach. And how it's linked with the water level. It was hard to find a data set of water level linked to the opening of the closing of a barrier beach. So for that reason, and also for time constraint, they were not included in this modeling effort.
That's great, Marianne. And a follow-up question from Jeff is, did any models include the loss of barrier beach forests, often large cottonwoods that help to anchor the shoreline?
Nope. It's the same answer than the first one.
And
phase two, Sharon.
Yes, hopefully there will be a phase 2 and 3 for this work as well. And a question from Jordan, in cases where wetlands are projected to decrease, was this because of low migration ability, or were there other factors as to why wetlands are decreasing in RCP 4.5?
There's also the elevation that limits the migration and the land use. But overall, when the water level increase, if there's a wetland loss, it's because the wetland are not able to migrate, because like they can endure a certain, they have a tolerance to higher water levels, but when it increases too much, they're going to be replaced by other wetland classes and or other open water. And yeah, it's the migration in our modeling. That's what it's the migration that limits the wetland loss.
Wonderful. And we have a question from Wes. He is wondering about invasive species and the modeling that you did. Marianne, you mentioned that you and Dominic will be presenting this Thursday on the invasive species modeling. Just wondering if you can give us a sneak peek, a brief synopsis of what we expect to hear this Thursday.
No, come. No, it's a joke. In fact, again, it's site specific, but I was really impressed by the modeling. It's showing how much we risk to be invaded by the end of the century if we have just because we are looking at the same climate change scenario. So there's a tremendous increase. If it's not cattle, it's Phragmites, and if we control cattail, it's going to be Phragmites. So yeah, that's going to be a really big challenge by the end of the century.
That's very interesting. And yes, please do come join us for this Thursday's presentation by Marianne and Dominic. So next question is from John with regards to inland marsh migration. Have you considered incorporating urban growth projections?
It's not that it's not considered, but it's not implemented in the CWRM. The land use, and let's say we're going to have twice the amount of house that we have right now around that wetlands. It's not included in the CWRM right now. We assume, we made the premise that it's going to be the same in the future that it is right now.
That's great. And a question from Susan Doka, whom you may be familiar with. This is very similar to coarser resolution work in early 2000s and later. That work did not include waves, but did include a SAISH, I believe. Have you compared and contrasted the projections between your high resolution or high computing power approach with the projections from the coarser resolution wetland vegetation output?
No, but it's a good suggestion. Yeah, no, we didn't do that.
Great, and looking forward to more information about those studies, Susan, if you'd like to share with us in the chat. And last question for Marianne and team before we move into the panel discussion. How can wetland conservation practitioners use this information? You've already alluded to some useful applications or potential useful applications of this work. Can you give us an example of how you see this information or this model being applied across the basin?
I will give an example. I received an email from Greg Mayne last week. I'm sorry, I don't remember the name of the wetland that he asked me, but it's a wetland that lost his Barry Beach not long time ago. And they are reconsidering maybe do we constrict it back, or what can we do with that problem? So using a tool like CWRM, you can make projections saying, okay, if I put back the Barry Beach, what will be the result? And if I keep it open, so it became an open abatement, what's going to be the evolution of the wetlands? And so we can take a decision, is it good money to invest in creating a Barry Beach again or not? I'm not here to say which answer is good for the society or for the ecology, but it's possible to compare different scenarios for those practitioners and make a decision.
That's great, Marianne. And we will actually take maybe two more questions before we move into the panel discussion, because I think these are most specific to your presentation. So we had a question from Rob. Will the models be available to the public?
The answer is yes. This is public work, so it should be available. Just like I said, the CWRM are standalone products, so it will be possible in the future to have access to some results. To have access to a model specifically, it could be more complicated. But let's say, for example, the DEM of the 26 sites, they are available. So somebody can ask to have access to those products.
Great. And our last question is, how were the years to transition from one wetland type to another estimated? For example, 2 years of dry conditions to transition from EM to shrubby swamp. How were those years estimated?
I will let Dominic answer to that, since he was the one tweaking it for a time.
Well, there's the base, like we use obviously a literature review on the different tolerance to adverse conditions for each wetland class. But we also had to fine tune the succession model in order to fit well with the observation. So we calibrate also the succession model. We also use observation data, and like we made some change to we made change to the succession model in order that it fit well. And also it's important to consider that this is not the first succession model that is used in the study. In the St. Lawrence River, we had a model that dates back to 2005 that is even more complicated than this one. And that was giving some very accurate results. So we also use the input of this research that is used in this one. And there's also a model that was used in the Rainy Namakan River in 2016. So yeah, we use previous work as input and literature review and observation. So it's a mix of a lot of things.
Wonderful. Thanks, Dominic. And now we will move into our panel discussion before the end of the webinar. I will now like to invite our speakers, all of them, to share their video and come online to join us for this panel discussion. Wonderful. And our first question is to Greg. Greg, looking back, what were some of the major challenges with completing the Assessing and Enhancing the Resilience of Great Lakes Coastal Wetlands project?
That's a good question. There's many challenges. Obviously, COVID was one of our biggest challenges, and I have to give it to some of our teammates that have newborn babies and we're bouncing them on their laps at nighttime while running the supercomputer. The complexity of this exercise, there's reasons why it took us this long. It is extremely complex. The amount of data that was generated the permission to access wetlands. In all honesty, vulnerability and resilience are still very theoretical concepts. So we had to operationalize that somehow. We had to find indicators and indices to express vulnerability, and you'll see more about that tomorrow. That was probably one of our biggest challenges. We really haven't done this type of work before on the Great Lakes using such rigor. So that's just a couple of responses, but it was well worth the effort.
That's great, Greg. And it's been such amazing work. We all look forward to the outputs as you finalize them. Our next question is to Frank. Frank, in simplest of terms, are you able to characterize or describe the rate and magnitude of water level changes to folks who might have missed the first part of your presentation?
Well, it really depends on many factors. And I think this is actually maybe answer another question that's there too. Depends on which lake you're talking about. Are we talking about average lakes? Are we talking average level? We're talking about the 1%, 5%, 50% exceedance level, things like that. Static lake level, there's also wind setup has been demonstrated as well. But and so the rate of change, the most important factor is throw it back to the person and say, so do you think that we're going to limit global mean temperature change to 1.5 degrees, 2.5, 2 degrees? Like, what's that going to be? Because that is going to be the major factor into kind of which RCP, which carbon sequence we follow, and that will be the the greatest predictor of where we go in the future. So all of this to say, there isn't an easy answer to that. There isn't an easy answer to say, oh, in 2030, all the lakes will be 3 centimeters higher. That just is not something we can say. It really depends on different people, different agencies, and what their risk tolerance, but also just what they believe the future will be. So I hope that was muddled enough to give an answer.
That was great, Frank. Thank you. And Frank, just to follow up, if you had unlimited resources and time, what would you want to do next with these projections?
Unlimited, get a handle. Here's actually what we would do. I just thought of a good answer for this. The one thing that we really think there could be the most improvement on is the representation of lakes in these models. So when we heard about lake level changes back in the 90s, when we talked about climate change, there were these, say, doomsday predictions of water levels at the time actually going down by like 3 or 4 meters. Like all the lakes are going to be dry. And we've attributed a lot of that is because just they had no lake model. So any increase in temperature was increasing evaporation, but it was really evaporation over the land surface. It wasn't actually a lake. And so it forecasted that the rate of change of evaporation would be a lot higher than the rate of change of precipitation. But what we found is that when we actually get these models that are small enough to resolve lakes, we actually get quite a different scenario. The rate of increase of the evaporation is not as sharp as it was in those earlier models. But still, even still, we're still using relatively simplistic models for the lakes. So there are what are called 3D lake models that do a very good job of simulating the lake. And lakes have different levels, of course, with temperatures and mixing and it goes beyond the seasons, it changes within the year. So it's very complicated. The problem is it takes a lot of resources as far as time, computer time. So it's actually at the moment, I don't know of any regional climate model that can actually incorporate a 3D lake model and have full what's called feedback into the atmosphere. And so if we could do that, then it would get the ice correct, and it would do a whole bunch. And to get the evaporation, you have to get the ice correct. So the ice cover. So that is what I would, if I had unlimited resources, build a computer that would be able to handle a 3D lake model inside a climate model. And we're tending towards that. They're like small experiments with, a few years, but to get these long simulations, it's going to take some time. So, hey, I had an actual answer. So with unlimited resources, that I think is the one spot where we could really improve the models.
It's wonderful, Frank. And to those of you listening, if you do know of any potential work underway, please do get in touch. We are always looking as local practitioners for improved and refined downscale climate projections. So our next question is for Marianne and the team. In your presentation, you've illustrated the utility of the coastal wetland response model and some potential gaps or future directions. Do you have some next steps planned for the CWRM?
I don't know if it can be official, but yes, we we will like in a we will I would say we will have different option for next type, but it would be nice to have the US side include Lake Superior. So Lake Superior, we start looking at the hydrodynamic modeling, but because of COVID and time constraint, we drop it. It's more profound, so it's complicated. I will add like faunal, but I will still not just faunal habitat, but I will look at the species level for some really indicative plants. I'm taking on wild rice, for example, that it's really interesting and maybe an interest for indigenous community, so that we can look at the habitat of a very specific plant instead of large class. And we are expecting that the CWRM can be used in other contexts than climate change. I'm thinking like in Lake Ontario that we can use it to evaluate future water level management plan, for example.
That's great. Thanks, Marianne. And wondering, recognizing that temperature wasn't part of the modeling, since you focused on waves and water levels, is there any indication from your research or from your experiences of how coastal wetlands might respond to changing temperatures as well?
Okay, so it's not included in our modeling effort right now, but water temperature will be imported for some wetland class, but mostly important, I will think at fish, spawning fish habitat. We are used to use temperature model in our team, but more for fish than wetlands. I don't know if you guys want to add something regarding temperature.
I think the growing season might change a little bit.
Oh yeah, that's a good point.
The temperature. If like I don't know, if the temperature is higher throughout the time season, the growing season might increase, and like this might affect the phenological stage of the plants, and affect the water level, might affect some critical stages more.
Good point.
Great answers. Thanks, Marianne and Dominic. And again, to Marianne and the team, you mentioned that the integrated ecosystem model can consider socioeconomic factors as well. Can you give us some examples of socioeconomic factors that can be integrated into the modeling, and what have you integrated or hope to integrate into the modeling?
Okay, so we have another project in the Lake Champlain and Richelieu River where we develop a similar approach, integrative approach than the CWRM. It's called IC for Integrated Socioeconomic Environmental System. So you have a wetland model that, like we show today, but we also include in that effort, in that integrative tool, we have residential damage, number of house, and damage in dollars. We have damage to infrastructure, public infrastructure, roads, commercial, and how you call it in English, I would say tourist activity, and so on and so on. We have social vulnerability also. So all the human population, is the population able to react to the flooding and so on. We also have some what we call indigenous interest performance indicators, such as the black ash, wild rice, and archaeological sites. And faunal habitat.
That's very interesting, Marianne.
Yeah.
And is any of that available publicly currently, or is there any way the public can access this information?
You mean regarding the IC system? I will read, I don't have the link right now, but we can redirect them to the International Joint Commission website. It's where we're going to post all our report regarding that project.
Wonderful. Thanks, Marianne. And a question to Frank is, Frank, I know you and several colleagues published a peer-reviewed journal article recently on navigating Great Lakes hydroclimate data. I'm wondering if you can give us a brief synopsis of what we might find in this paper.
Wow, okay. The big thing you would find would be a link to greatlakescc.org. I don't know, I can probably post that in the chat as well. So what it was just, we have a lot of good information. I mentioned that there's this collaboration between Canada and US federal researchers, and working with the US Army Corps of Engineers, NOAA, and the USGS. So we have a website and we basically present our data there. So what this paper did was just try to say, okay, to people in the greater research community, because we found that a lot of the stuff we do isn't really out there in a lot of the research community. So we wanted to say, hey, research community, if you want to look for, you know, precipitation over the Great Lakes, here's like the best source of it, or here are some sources of it. And so the paper basically lists the different hydroclimate variables that we have some compilations of, their sources, errors, things like that, but more importantly, where they could get them. So if you look at the paper, there are different sources. Most of them go to the coordinating committee of the Great Lakes website, which I just mentioned, and I'll post on the chat. And yeah, so that's what that's the basic rundown of the paper. And then there are just details on the different data sets and how they can be used by others.
That's wonderful. It's such a great resource. Thanks, Frank. And another question to you is whether you have considered modeling ice cover, and whether you can speak to how ice cover is expected to change across the Great Lakes as well.
Yes, so that's one variable that we didn't talk about today. It doesn't directly affect lake levels, I'll say that. It of course affects the amount of evaporation, which affects the lake level. So we didn't present it here. It does kind of is part of the analysis, but it's again not directly related to lake level. So hopefully in the future, again, we were hoping to compare some different lake models, and we can actually compare how they do simulating the ice in the past, and then we can have more confidence in how they simulate into the future. So that is definitely one of our next steps, is to look more in detail at the lake models, and one of the variables will be the ice cover.
That's wonderful. Thanks, Frank, and looking forward to that work. Circling back to Greg, Greg as the lead of this project, how would you like to see the climate projections and water level projections, as well as the CWRM, used and applied by local wetland practitioners?
Sure, good question. There's obviously some needs out there. Climate impacts are already visible. We know that there's wetlands that have already been severely degraded, and even diked wetlands have been breached. So it would be informative to apply the results of the modeling exercise, also the sensitivity and in general, the entire vulnerability assessment to some of these wetlands, and work with local groups. The rubber hits the road really when we speak with the municipalities and local stakeholders and partners. We have to get their buy-in and their interests factored into this and move on accordingly. Hopefully we can find some opportunities for implementation and use all the science that we've generated and apply it to some of the local wetlands. So fingers crossed that'll happen.
That's great. And Greg, I know throughout this 5-year project, you've undertaken numerous stakeholder and rights holder engagements. Can you share with us what you have heard throughout these engagements and the level of interest in this project?
The level of interest is extremely high. Absolutely. From day one, we had large workshops that attracted over 100 individuals. Thanks to you, Sharon, you helped host those. Coastal wetlands, I think, have always been an interest to Great Lakes partners and stakeholders. So this isn't too surprising that this particular project is of equal interest. Where can I go from there? Did I answer that question?
You did, yes. And we've already received lots of questions about when the reports and the models will be available. So Greg, I know you'll be touching on that as well in our closing slides. I'd like to open it up to anyone with any parting thoughts before we close the webinar today. Marianne and Frank, anything you'd like to add before we close?
I think we just want to be thankful. It was tremendous work, but it was also a really amazing opportunity for young practitioners as us, for young scientists to be involved in such huge effort. So most of us were just going out the university. So yeah, I'm really glad we had the chance to be a big part of that that project. Hope we can keep it.
That's great. And so I will share my last few slides in closing. That brings us to the end of our panel discussion. Thank you to all of our speakers for your excellent presentations today and for your ongoing work. I would also like to thank our project team, Greg, Anders, and Patrick from ECCC, and Megan, Jessica, and Krista from TRCA for making this webinar possible. For questions that we were not able to cover within our time, we will follow up with speakers for some brief written responses, which we will share along with the presentation slides and webinar recording. We anticipate that the slides and recording will be available in a couple of weeks following the webinar series, so please keep an eye out for an email. We also have 4 webinars over the course of the week, and we hope to see you at these upcoming sessions. Again, the session tomorrow will focus on sharing the results remaining results of ECCC's climate change vulnerability assessment. So we hope you're able to join us to hear about the rest of the vulnerability assessment tomorrow. I will now call on Greg to say a few last words and share some upcoming reports and resources as well.
Thanks, Sharon. So first, an acknowledgement to the staff from the Meteorological Service of Canada from both Ontario and Quebec, and really to express my respect and appreciation for the attention to detail. It's a huge amount of work that was involved in all of the modeling. So thank you very much. It not only provides interesting results, but also identifies some information gaps. And we've touched on a few of those information gaps that we might want to follow up on, such as diked wetlands and barrier protected wetlands. Frank and Marianne, they mentioned that they've completed some technical reports. I should mention that these technical reports have gone through peer reviews and they're almost completed. I'll say this again, but we have a number of reports associated with this project, all of which will be made available to the public. So the first 3 that are outlined on this slide represent Frank's work, Marianne's work, and because we obtained such an enormous amount of information from downscaled climate modeling, lake levels, etc., we worked with, again, Sharon and her staff at TRCA, but also Annex 9. And this is an Annex 9 product, climate change in the Great Lakes Basin. So that's yet another report that we can anticipate in the near future. And then as we go through the subsequent days of the week and the sessions, you'll listen to sensitivity, adaptive capacity, and of course, solutions to enhance Great Lakes coastal wetland resilience. All of these reports will be packaged and made available to the public, hopefully at the same time, but later this year. So with that, just thanks to everyone for sticking with us. It's been very complex and detailed. Just the mere fact that you've stayed with us shows us that you're very keen and interested in coastal wetland conservation. So thank you very much.
That's wonderful. Thank you for those closing remarks, Greg. Thank you everyone for joining us, and take care.
Thanks, Sharon.
Thank you, Sharon.